Hello, Dr. T. This is my methods assignment on finger photoplasmography. I hope you enjoy. The contents of this presentation will include a description of the technique for finger photoplasmography, as well as talking a bit about the instrumentation process, limitations, and applied research context in the Human Vascular Control Lab with Stu and Ladd. Finger photoplasmography, or PPG technique. Finepress Medical Systems develops clinical devices for continuous, non-invasive blood pressure measurement and hemodynamic monitoring, including the finger PPG and phenometer. Hemodynamic variables such as systolic and diastolic blood pressure, heart rate, stroke volume, and thus cardiac output are measured and/or estimated. The system functions via the volume clamp method. In essence, the finger cuff placed on the participant's finger measures arterial pulse. As the heart beats, blood pressure results in alterations to the diameter of arterioles detected by means of an infrared PPG built into the finger cuff. However, the cuff prevents this by regulating the diameter with dynamic pulsatile unloading. During systole, for example, if the arterial blood pressure increases, the cuff pressure will rapidly increase to prevent diameter changes, allowing maintenance of an unloaded state, that is, held at zero transmural pressure. This way, the arterioles are kept in a uniform diameter, allowing researchers or clinicians to measure intra-arterial pressure and hemodynamic variables at a constant arterial diameter, as the pressure inside the cuff that is needed to maintain this equilibrium resembles the arterial blood pressure in the finger. Notably, the phenometer estimates cardiac output from the patented model flow method. This describes analyzing the arterial pulse wave data and using mathematical algorithms to derive central pressure waveforms from the peripheral measurements obtained by the finger cuff. Moreover, one of the advantages of the phenometer is its ability to provide continuous beat-to-beat measurements of blood pressure and other hemodynamic parameters. This allows for real-time monitoring of cardiovascular functions. Instrumentation process. The main components of the finger cuff are an inflatable air bladder and a plasmograph consisting of a light source, that is, infrared light emitting diode, and a light detector, that is, an infrared photodiode. The air bladder is connected to the front end unit via an air hose and both components of the infrared plasmograph via a cuff cable. The front end unit is connected to the main unit and a pump unit in the phenometer. First, the front end unit should be fastened to the participant as demonstrated. Next, the researcher must measure the middle phalanx of the middle finger to determine a cuff size. Medium is observed. Then, select an appropriate cuff and begin to secure onto the patient's hand. A supinated position is recommended here. Next, ensure the light sensor monitors, indicated by the gray circles on the cuff, are positioned on the medial and lateral aspect of the middle phalanx. Then, secure the finger cuff and attach the associated cords to the front end unit. To continue, participant data, including their gender, age, height, and weight, are inputted into the phenometer. Next, BeatScope software will be used to start the phenometer and finger plasmograph. First, we need to name the file, then press Start. Here, we should forewarn the participant that the air sac in the finger cuff will begin to inflate. Then, press Start on the phenometer unit. If properly set, the BeatScope software will indicate the signal to be great, good, or excellent. In any of these cases, recalibration will occur incrementally. Data can be observed on the phenometer unit or the BeatScope software, where hemodynamic variables are continuously measured. Otherwise, if poorly set, the BeatScope will recalibrate repeatedly in few increments of 10 or less heartbeats until eventually stopping cuff inflation and requiring a reset. Limitations. As previously stated, The phenometer and finger PPG must be properly affixed to the participant. Also, note that the hand and fingers should be at heart level, as above heart conditions decrease blood flow and below heart conditions will increase flow. Also, during data collection, the hand must remain limp, that is, without any muscle activation, to the best of the participant's ability. This is to reduce variations in blood pressure and increase clarity of the arterial readings. Otherwise, the signal may be inaccurate and unreliable. Further, finger PPG is sensitive to differences in temperature. That is, if the participant has a cold finger, for example, reduced blood flow and vasoconstriction could be observed, leading to poor measurements. Compromised circulation or peripheral arterial diseases are also known to disrupt the accuracy of finger PPG. Reduced blood flow and/or dysfunctional arterioles would affect characteristics of blood pressure used to estimate hemodynamics. In general, the phenometer and PPG are limited in their sensitivity to noise, which can disrupt the signal and present challenges with data collection. Overall, literature has described the phenometer technology as accurate and precise in measuring heart rate, and accurate but not precise in measuring systolic blood pressure, diastolic blood pressure, and cardiac output. In this way, while the estimations are reliable, this non-invasive measure may not be as accurate as gold standard invasive collection. Applied research context. Now that we've described finger PPG and phenometer technology, let's explore its place in the Human Vascular Control Lab in Stu Mladen's research. Stu is interested in compromising limb perfusion to study the effects on cardiac output and other hemodynamic variables during exercise. Specifically, Stu aims to determine whether cuff inflation compromises exercising limb perfusion and flow. Essentially, does blood flow restriction actually restrict blood flow in exercise? Participants are positioned in a seated upright position while Stu measures their femoral artery, mean blood velocity at rest and during exercise. The modified cycle ergometer allows minimal thigh movement, allowing clear data recording via Doppler ultrasound. Understandably, an accurate, non-invasive measurement of arterial blood pressure, heart rate, stroke volume, and cardiac output is indispensable in Stu's study. This way, he can compare data through trials of differing blood flow restriction to gain insight on exercising limb hemodynamics and total circuit flow. Thank you for your attention during the presentation, Dr. T. Obviously, this is just a snapshot of what finger photoplasmography has to offer, and very briefly going into some of the technology involved in the device. Regardless, I hope you enjoyed the presentation and have a great rest of your day.